All right, so this is micro 1, the 5th lecture. And next week, so we'll do one more Zoom lecture, and that will be Thursday. And then next week, we'll be in class. And I didn't look at the schedule to see what room it is, but it's on the schedule. It's a little harder to find than it used to be. You have to scroll over. Let me just so a couple of housekeeping details. So one, a lot of students, I think we have 18 students out of the 90 students that did not pick up their boards last week, and that's fine. You can pick them up this week. It only takes you about 20 minutes to solder on the parts because there's only 8 parts to solder on. Make sure if you have any questions about soldering on the part, make sure that you and be sure and mute your microphone if you're not muted. Okay, yeah, there we go. I can do that. So anyway, what I recommend, if you have any problems at all soldering them on, just stop, bring your board in, and we'll help you. If you miss solder a part, don't try and fix it yourself. Bring it in, and I have fancy equipment to make it easy to desolder. If you try and desolder it yourself with multiple pins, you will inevitably damage your board. And one student already did, and there are no spares. I made 91 boards. I only had 100 chips. We went through well, I guess we went through 9 of them or 8 of them on our test boards. And so I only have 91 boards. And actually I gave one to Jonathan, who teaches, well, he teaches a couple of courses, but anyway, I gave it to Jonathan, and so he's playing with it right now. So I don't even have a single spare board. So if you do damage your board, no problem. I can probably fix it. I've never had a board so damaged I couldn't fix. But I do have more printed circuit boards. I just don't have any more chips. So we could theoretically make another board for you and then take the chip off your board and move it to another one. But that's taking the chip off is there's some chance of damaging it, although I've done it a bunch and I damaged a few, but mostly I can do it successfully without too much trouble. And again, for that, we use special tools. For instance, I have a hot air gun, and I'll show you what that looks like. Let me share my screen. And let's see. Yeah, we'll share this one. And then we'll pop this up. So you can see, so here's a hot air device. Well, yeah, I don't know if you can see it or not. You can see how it has these fluted openings, and that puts heat on exactly the right places to mobilize the chip. So that works pretty well. And then I also have a device that sucks the solder off. It has a little motor with a vacuum. It heats this up. There's a little hole in that tip, which you can barely see right there. And you put that over the pin, heats up the solder, and then you hit the button here on the side, and it starts the little pump, the air pump, and it pulls a vacuum and it sucks the solder right out because the solder is liquid when it's melted. Okay, so anyway, so if you mess your board up, or if you have any questions at all, just don't do it. Bring it in, and we'll fix it. We'll help you get it done. It's not that difficult. It probably takes me less than 6 or 7 minutes to solder on all the parts. So anyway, we're only soldering on the parts that pertain to the PIC initially here. Then later on, we'll solder on the parts that pertain to the ATmega 328 PB. And when we do that, we'll show you how to hook up the cap that we left out of the circuit that allows it to be used with the Arduino IDE. You can program it with the ISP programmer, but most of you won't have one of those. And so but you'll be able to program it directly from the Arduino IDE with the CP2102 dongle that we'll also give you later on. Okay, the other thing I will have this Friday, and we'll keep track of who's gotten one, but I'll give snaps to everybody who's purchased a board. We'll just give you the snap, and we'll give you a cable to go with it. So let me show you what the snap looks like. So the snap comes in a little box like this, and you pop it open, and it comes out, and it's in a little anti-static bag like that. And if you take it out of the anti-static bag, eventually you can get it out of the anti-static bag. This is what it looks like. And I do have cases, although I was so busy I didn't really print up a whole bunch more. So, but maybe during the semester I'll print up some cases, and we'll give you a case as well. The cable, the USB micro cable plugs in here and then into your desktop or laptop, and this plugs into your board. And the way that looks is just like this, right next to the UTSA logo. Or these are, by the way, it's not just a logo, these are actually touch buttons. So the snap actually plugs in right here. And there's a little arrow on the snap that has to be aligned with the little arrow on the board. And if you get those all lined up, then the snap will program it just fine. I currently have the CP2102, and you can plug it into that slot if you're going to use your Arduino, or you can plug it in down here to this slot if you're going to use the PIC. And now you can talk to the PIC. I don't know why it's not working in Arduino. Oh, yeah, oh, it is. Yeah, probably. Yeah. Okay. And then, like in this case, I've wired up this little OLED display, and it's doing this little Adafruit demonstration program. Now, I have code to run this same display off of the PIC. And in fact, the PIC and the our ATmega 328 are connected with the I2C lines. So those lines are common to both chips, and that's how they'll communicate with each other. And so I have pretty good expertise with our PIC chip. I pretty much have used and know all the features on it, and I'm pretty good with it. But the ATmega 328 and the Arduino IDE, I'm still sort of learning about. And so it's going to take a little bit to develop the code, but eventually, by the time we get to it, I'll have some code all set up so that we can have the two chips talk to each other, and we'll do at least one lab and maybe more where the chips talk to each other. And then we'll also hopefully give you a good example of a final project where you will use both chips. You can use the Arduino IDE and the ATmega 328 IDE chip.
It seems like it.
Go ahead. Question? All right. Well, anyway, and you can see, and then this is just the snowfall that after you go through all the demo things, and it just runs this. These little displays are kind of cool, and they're easy to use with the Arduino. And you can also, I have code makes it fairly easy to use with the PIC. Occasionally students will develop games on these that are kind of fun. That takes a little more programming. Okay, so let me get to the heart of the matter then. So this Friday you will get a snap, and hopefully then you'll be able to plug this into the header for the PIC lined up like this, and you'll be able to program the PIC. Make sure if you have any questions about soldering on parts, bring your board in, and you need to bring your board in anyway, but bring it in and we'll fix it for you, or we'll get it all set up. And if you've already damaged a little bit, don't worry, we can generally fix that. There are some things that are hard to fix, like if you tear the Arduino IDE off the board and rip up some of those pads, okay, that's probably not fixable. I do have some spare boards though, so we'll make that work. Okay, so those were some of the announcements. I would like everybody to try and come to lab on Friday. This is important. If you do the lab on Friday, this is going to really help you in the course. Okay, let me, so what I'm going to do now, let me share my screen again, and we'll get started kind of with the lecture. Just wanted to go through those announcements. All right, so here's our syllabus, and we're here on the 1st of February. Can't believe January's already gone. And I'm going to talk some more about assembly language programming. And I may or may not get to the demo, but what I will do on Thursday, I will go through again how to do lab 1. And so when you come in, if you've got your board all soldered up and when you get your snap, you'll be able to sit down and do your lab. Okay. So what I want to do today though is I want to continue to talk about assembly language programming and how that all works. Okay, so I'm going to switch from here and I'm going to share my other screen. So I'm going to go over the instruction set. And again, if you look at the data sheet, before I show you where the instruction set is, again, because I've been there before, but I want to talk a little bit about this block diagram, which is in the device overview chapter. What I want to point out here is that we have an instruction register. Well, here's our flash program memory. So this is where the program, when you compile the program or assemble it, depending on whether you're doing assembler or C, once the bit file gets set up, which will be always in assembler, that's what the chip runs. So even when you write a C program, the C program gets compiled into assembler, and the assembler gets assembled into a bit file that gets loaded. So the bit file is going to reside in this flash program memory. This flash program memory is 14 bits wide. You can see this path shows that it's 14 bits. And there's a program counter right here, and this program counter has 15 address lines that address the address lines of this program memory. The data lines are connected to the instruction register and then to this program memory read register and some other things. When the program counter, say you have an instruction at location 10, the program counter sends out address 10. Address 10 appears on the data lines out of this flash memory and gets latched into the instruction register. And that would be a 14-bit word, which then constitutes the instruction. Now, there are several types of instructions. We went through this already, but some of the most common instructions contain within them an address of a register or a memory location that you're going to work with. And the way that works is, if you remember, you have to use a bank cell if it's not one of the core registers or not one of the common RAMs in the upper 16 bits of the first bank. But all the rest of the registers, all the special purpose registers for each of the modules, and all the common random access locations all have 12-bit addresses. Of those addresses, the upper 5 bits have to be properly loaded in the bank select register, which is accomplished by using the bank cell assembler directive. The other 7 bits come out of the instruction register, and they're combined with the upper 5 bits, and they go into this address multiplexer then that sends a 12-bit address into RAM, depending on what you're doing. So it could come from one of the indirect addressing registers, which we're not using with assembler, but we could. I mean, they're available. We just for simplicity's sake, we're kind of skipping it. But C, this is all C uses. But we're gonna use the direct addressing, and in direct addressing, 7 bits of the address are stored in the instruction register, and the upper 5 bits have to be preloaded in the BSR with a bank cell, unless it's one of those registers that's mapped to every bank, in which case it doesn't matter what's in the BSR, it will still get the right location. And that's how we address RAM. And then the RAM sends the data out. Typically that data then goes out and goes into the arithmetic, multiplexed into the ALU, depending on if it's going to be if it's going to be added or ANDed or ORed or exclusive ORed with W or subtracted, or it goes into W if we're going to just take the data out of the RAM and put it into W. And then it can be put back into the ALU. And then from the ALU, then it can go back into random access memory. These pathways are bidirectional here. Okay, you can also write the program counter, and there's a number of things you can do. All right, so what I wanted you to see though was that the lower 7 bits come out of the instruction register, and the upper 5 bits come out of the BSR, and that's what this shows. All right, let's go down and look at chapter 29, the instruction set. Now, again, remember there are these little characters that help us understand what the instructions are. There's an F that stands for a file register, and that's only 7 bits. Then there's it's actually a 12-bit address, but there's only 7 bits put in the instruction. Then we have the W register, so that's what W stands for. That's our one general purpose working register. Then we have a B, which is a 3-bit field that gives us a bit address within an 8-bit file register. Within 1 byte, this 3 bits of B tells us which bit we're actually dealing with. And that's what we use for a bit clear F or bit set F instruction, or for a bit test F instruction. Bit test F skip set, bit test F skip clear. Then we have this K, which is a literal field, and it's usually a constant, or it could be a label if in the case of a go to instruction. We use this when we want to put a constant value in the W register to then write it into a register to configure some module on the chip. We've already talked about this with the oscillator control register. We want to set the chip to run at 4 megahertz, and there's a certain value, hex 6 alpha, that we have to write into the W register, and then write from the W register into OSCON. Since OSCON is not mapped to every bank, we have to make sure we do a bank cell on OSCON before we then do the move W to F instruction, which takes the 7 bits, the lower 7 bits of the OSCON address out of the instruction register, and takes the upper 5 bits out of the BSR to get us to the right place. Okay, and then we have this, we have this don't care. Then we have this D, which is a single bit, and it specifies in most of our byte operations whether we leave the result in the W register or we leave the result in the F register referenced by the instruction. Now, there are a couple of instructions that don't have this D bit. One of those is move W to F, and then another one is clear F. So in the case of clear F or move W to F, the destination is always the file register. And by default, if we don't specify D in the instructions that have D, it will always be by default the file register if you don't specify. So you have to keep that in mind, and you should not forget to specify. Okay, and then finally, there's a couple of some of this indirect stuff has you can pick which file select register you're pointing to, either 0 or 1, and you can also do some pre and post increment decrement on the indirect addresses. All right, and then here are some of the bits that can be affected: program counter, the timeout bit, the carry bit, the digit carry bit, the 0 bit, and the power down bit. All right, so here are the formats, and we went through these already, but it's always good to repeat a little bit. So most of the byte-oriented instructions look like this. They've got an opcode. That opcode could be add, could be subtract, could be add with carry, could be subtract with borrow, which is the carry. It could be complement, which means invert every bit. It could be and the addressed register with the W register. So the contents of F are ANDed with the contents of W, just like are the contents of F are added with the contents of W, or subtracted from, so added with carry, subtracted with carry. Or they could be exclusive ORed or rate or inclusive ORed, or they could be and you can swap the nibbles. You can swap the lower 4 bits with the upper 4 bits. And I think that's, and cleared, you can clear it. But the clear instruction is a different one because it doesn't have the D bit. Okay. Then there are some bit-oriented instructions. There are 4 of those. We'll look at those in a second, where we specify a 3-bit value and an F register. Again, the F still has 7 bits, but the additional 3-bit B variable operand, which is not the file register is always the first operand if there's a file register reference, and then the D bit and the B bit are the second operands. So the actual way they're stored in the instruction is slightly different than how we write them. And then we have this literal operation where we will take W and we can either store this literal, this 8 bits of K into W, or we can AND W with the 8 bits of K and store that in W, or we can OR the 8 bits of K, or we can exclusive or we can, I don't know, I forget. There's, we'll look at those in just a second. I think that's mostly what we have. And then there's a couple of special ones where we, well, these are the call a subroutine and go to, and this K is now an 11-bit address. We also have then these 2 unique ones. This is move the 7-bit literal into the program counter latch high. And then this is move the 5-bit literal into the bank select register, the BSR. This is the instruction that gets generated by the bank compiler or assembler directly. And then finally, we have a branch always, which is essentially the same as the go to instruction as far as what it does, but it has a smaller address. Its literal address here is 11 bits, and here it's only 9 bits. So it's only got a quarter of the addressing ability. And remember, these are 2's complement values, so they go backwards and forwards. So you can only go forward in the code. And say in the case of 9 bits, you can basically only go forward 256 instructions, or 255, I guess. All right, and then we have, these are file select register. These are indirect addressing codes, so you can just kind of ignore those. And then finally, there are some opcodes that take up all 14 bits, just because they don't need any operands, so we just let them expand to 14 bits. Okay, so those are the different types. Now, let's see. So this first group are the byte-oriented file register operations. Again, add W to F, add W to F with carry, and W with F. Arithmetic shift right, oh, I forgot the shifts. So arithmetic shift right, logical shift right, logical shift left. And we don't have a arithmetic shift left because it's the same. So the arithmetic shift, the arithmetic shift right replicates the higher order bits. So that's how that works. And then we have clear F, clear W, then complement F, so that just inverts every bit. And then we have, oh, yeah, decrement and increment. So you can subtract 1 from F, you can increment F by 1. You can inclusive OR W with F. You can exclusive OR W with F down here. And then you can move F. Move F basically takes F and puts it into the W register. Or if the D bit is a 1, all it does is moves it back into the same file register, but evaluates, but it does set the Z bit over here. And this column tells what bits are affected. notice for the most part, the carry, the digit carry, and the Z bit are only active when we're doing mathematical operations like addition and subtraction. But we do, the Z bit does get involved, the carry bit does get involved. The Z and the carry bit do get involved in these shift operations as well. And then some instructions, most of the instructions affect the 0 bit. And the rotate instructions just affect the carry bit, they don't affect the 0 bit. Okay, so as you look at these, notice that all of them do have that second operand, except for the MOVWF. That moves W to F. So obviously there's no point in leaving in an instruction that's supposed to move W to F to leave it in W. So that wouldn't make any sense. That would do nothing really. And then this one, clear W, well, obviously that affects W, and clear F, obviously that affects F. So those are the ones with only with no destination bit, and this clear W doesn't even have a file register selected because obviously it only affects the W register. Okay, now we have 2 byte oriented skip operations. Now the decrement F skip on 0 is very, very important. We're gonna look at how that allows us to write an assembly language for loop. The increment F skip on 0, we don't kind of use too much. You could use it, I guess, if you were indexing your way through an array from the bottom up, and you were using the increment function to do that. And then when you got you had positioned the array so that it would overflow at the top. That would be tricky, but I guess you could do it. Anyway, this could be one case where you might use it, but mostly the decrement F skip on 0 is what we use. And when we finally decrement it and the 0 bit gets set during that decrement, well, I guess it doesn't actually set the 0 bit, but but when it zeroes out the F value, it skips the next instruction. Surprising that it doesn't affect the 0 bit. And then we have, so these are also deal with whole bytes. Okay, then we have the bit oriented instructions. There's really 4 of them. There's the bit clear F, bit set F, and this has a file register and a B second operand, which is a 3-bit field that says whether it's bit 0, 1, 2, 3, 4, 5, 6, or 7 that's going to be affected. All the other bits are ignored, not changed, not harmed in any way, but the bit selected will be either cleared or set depending on which instruction. And down here, we can use what's called the bit test F skip clear and bit test F skip set. This is where we can check a pin in a port that may be connected to, say, an input switch, or it may be connected to some other logic. And when that logic sends out a 1, well, it was sending out a 0, and now it sends out a 1, then, then our program can detect that and go on to the next thing. Then finally, we have these literal operations. And these are so the operations we can do with W are add a literal to W, add and a literal with W, inclusive or a literal with W, move a smaller, move a 5-bit literal to the BSR, move a 7-bit literal to the PC Lath high, because it only has 7 bits, because we have a lower 8 bits, upper 7, that gives us 15 bits in our 15 bits in our program counter. Remember, we only have 32K maximum in our program memory. We don't have 32K on this chip. We only have 8K, but this family could have 32K in a chip. All right, and then finally we have this move literal to W, and we'll use this quite a bit to configure our various registers. We basically have the constant we're going to load into W is embedded directly into the instruction. And it takes that data, that 8 bits of data, and puts it in W. And then here, it takes that 8 bits of data and subtracts either W, well, subtracts W from the literal. And then here, we exclusive OR W with the literal. But in all these cases where we do an operation with W and the literal, the result winds up in the W register because there's no other register involved. All right. So those are, and then the only thing left, we have these branch instructions and call the subroutine. And we have it, we can call the subroutine and just call it, and we can call it with W, where we can send the value of W to the subroutine. And then we have go to and branch always. And then there is this relative branch with W, which I haven't used. But anyway, this is an opcode only instruction. There is no operand. Obviously, it does involve W though. But normally I just use usually I use the go to. And really, there's nothing that the go to can do that there's nothing the branch always can do that the go to can't do. So there's really I don't even know why they have the branch always. Probably legacy instruction. Okay, and then we have return from interrupt and return from and then so this is the only return from interrupt. This return with a literal and W, and this return from subroutine. Those are both returns from subroutines. So you can come back from a subroutine with a value saved and left in the W register. All right. And then here's some kind of funny operations. Some of these are legacy things. So there's a clear the watchdog timer. We'll talk about how the watchdog timer works. Here's a no operation instruction. We already looked at that briefly. It's just a placeholder. It takes one instruction cycle, but it does nothing. And then this option and tris register instructions, these are legacy instructions, don't use them. And then reset basically just makes the chip reset. So sometimes we'll use that in an error condition to just reset the chip. And then sleep, if we execute this instruction, it puts the processor to sleep, and then we have to wake it up in a number of different ways. And we will do a sleep lab, and you'll see several different ways to wake up the chip. And then finally, there are these compiler optimize, C compiler optimize instructions to basically help it work a little more efficiently with the C language. And you can use these in assembly language, but we won't use them because they're a little more complicated, don't really fit what we're doing. Okay. Does anybody have any questions? So we've been over this twice now. So hopefully you're getting a mental picture. This is the entire 48 instructions in the assembly language instruction set. This is all you can do. There are no other things you can do with this processor. This is it. And there certainly are limits, but there are also some nice features. But this does allow you to write some pretty complicated programs. Now, of course, we will normally use C, but the C just gets compiled into these instructions, and then these instructions get assembled and loaded into the chip. Okay, so now what I'm going to do, I'm going to look at some of these critical instructions. So, and the ones that are really important, we're going to use MoveF quite a bit. That's where we get a value from a random access memory location or from a special function register, and we load that into W. Then we're also going to use the move W to F, where we take what's in W and we store it in a memory location. Now notice that the MoveF does have that destination bit. You do have to put a 0 there or a W for the W register. Either one's legal. Otherwise, by default, you won't move anything. So you have to remember that second operand for the MoveF instruction. For the MOVWF instruction, you don't have to worry about that operand. You just put the data register address in here, the lower 7 bits, but you do have to remember to do a bank cell on the register to put the upper 5 bits in the BSR before you execute this. All the rest of them, except for this clear W and this clear F, have that destination bit. So if you do add W to F, you have to specify whether that result gets left in W or gets left in the file register. And it depends on what you're doing, why you might want to pick one or the other. Okay, so the two most important here are move F and move W to F. And then we have to deal with, we use this decrement F skip on 0 quite a bit. We also use the bit clear F and bit set F instructions pretty frequently. And then we also use these bit test F skip clear, bit test F skip set instructions as well. And then some of the rest of these things, they're the most important one here is typically move literal to W. Now, sometimes we will use one of these others, but it's pretty rare. The most commonly used one here is the move literal to W, and of course, the compiler directive uses the MOVLB, the move literal to BSR. Again, the literal in this instruction is only 5 bits, and this literal in the PC latch high is only 7 bits. It's not 8 bits. All right, so that's it. You will use the go to and the call, and usually without returning stuff in W. We'll just use the go to and the call. And we might use the no op in the sleep study. We are going to use sleep in TRS. We're going to do the function of this tris instruction, but this is a legacy instruction that we're not going to really use, so don't worry about it. Okay, so let me switch now to, let's see, I'll stop this. Let me stop and see, does anybody have any questions about the general overview of the instruction set? And now I'm going to show you how we do certain specific things in assembly language. And these are the things I'm going to test you on in the assembly language programming test. So you want to pay attention and keep track of this. Questions before I jump into that? Okay, so let me share my screen again, and I will shift to this. All right, can everybody see this?
Yes.
Yes.
Okay, so this is what your board looks like. And this was, I think I soldered all the parts onto this board, some of which we may never use. This little header here was actually designed for the OLED display that I demonstrated earlier. Well, what I've actually plugged it into over here on this side is also the I2C header. So we have two I2C headers, this one and this one. Our intent was to make this exactly line up so we could just plug this display right in over here. But we screwed it up and 2 of the pins are swapped, and so you can't plug it in directly. You have to use the jumper wires. And this one, we could have lined up that way, but my intent on this one is to have it set up so we can plug the 2-line-by-16 LCD display directly into that. And I believe it is set up that way. Let me just, let's see. Let me just check that real quick. Let's see. Got one something. Well, oh golly. All right, give me 1 second. I'm just gonna let me go grab one. Okay. So here's what the 2 line by 16 LCD display looks like. Looks like this. And it has an LCD display that displays 2 lines and 16 characters per line. So 32 characters all total. And if you flip it over, it has a little daughter board attached to the back of it. And this daughter board provides the I2C interface to this display. So you can program it and control it with I2C. And let me just see if in fact, yeah, so you can theoretically, anyway, you could theoretically plug it directly in like this. It's lined up correctly for that. It's going to be standing up, but we might try and do that. That's, that should work. It's the, yep, exactly the right pin out. Ideally, what we would do is instead of having these right angle pins, I'd have straight pins, and then we could plug it in like that. And I think I can modify these. Well, so I'll probably just modify these by bending them or something. Anyway, we'll think about it. I hadn't really gotten to this point with the display, but that was the idea. I suppose what we really should have done is use a right angle female header, and then you could plug it in straight like this with no modification. And maybe that's what I'll do. We are gonna have to order a new set of boards for the fall and make some modifications to them, and that's probably one mod we'll do. Okay, well, that's not a mod really. We just have to order some of those. I don't have any female right angles, so we'll have to order those up. Okay. All right, so that's that. All right, I'm going to dispense with this, and we're going to write some code. All right, so the instructions I'm just going to go through. Probably the easiest way to do this is just to talk about how we would swap 2 variables from one location in random access memory to another. So let's say we have 2 locations in RAM. Now, if you'll remember, we have our RAM is divided into banks, and we have 80 bytes in each bank, and then at the top of each bank, we have the upper 16 from the bank 0 mapped into every other bank. So the upper 16 in every bank are the actual upper 16 in bank 0, and they're just mapped to every bank. So they're not. So if you put something in the upper 16 in bank 0, and then you want to put something different in the upper 16 in bank 1, you're talking about the same location. So it's not going to be, you're going to overwrite stuff if you do that. Okay. Now, so let's say we have let's say here's bank 0, and in bank 0, starting at location 0x20, that's our first random access memory location. And so let's say for sake of argument, we want to put say the value of 0x 53 hex. Okay, so 53 hex there. Maybe I don't even, yeah, that's probably okay. Let me do a smaller number. Well, okay, we'll leave it at 53. All right, and let's say we have location 21, and we want to put 0x 26. And then let's say we're going to use another location, 0x22, and we don't care what's there. We're going to use that as a scratch register. So we'll just use this as a kind of a place we can store something temporarily. All right. So the first thing we have to do is when this program's loaded, we won't have 53 in this location. It'll just be some random value. So what we do is we first have to preload. So we'll put in a comment, preload, and we'll call this register. We're going to give these names. We're going to call this XX, and this YY, and this ZZ. Now, the reason I don't call them X, Y, and Z is because Z is a reserved character, stands for the 0 bit. So we can't use just Z. So I call them all three XX, YY, ZZ. We could use X and Y, they're okay. But the Z by itself would be a problem. The compiler would give you an error for that. The assembler would give you an error. All right. So the first thing we're going to do then is we're going to define these locations. We can do that a whole bunch of different ways. We can use several different compiler directives. Probably the easiest way, though, is to do a C block. And we'll start the C block at this address, 0x20. Now, here's one thing that's really important. You have to keep clear in your mind the difference between an address and data. These are the addresses, 20, 21, and 22. This is the data, 0x53, 0x26, and nothing. So if you get these confused, which many students do, you'll mess up the test because you'll be trying to use the address as the data or the data as the address, and it doesn't work. The address is the actual location in memory where these random access bytes are stored. The data is the bit settings at that location of the bits in the byte. So again, the address is the location and the data is the contents at that location. Always keep this straight in your mind when you're coding. Now, eventually it'll be second nature. You'll understand this. It's the same thing in C, but it's a little, for some reason, because you're not dealing with numerical addresses, people don't get this messed up. In C, all the variables have names. We can see what the actual address is in memory, and that's the ampersand operator. But normally we only care about that to assign it to a pointer, so we never actually look at it. We just might assign it to a pointer. But in assembly language, we do know what address they're at. Typically, we can write assembly code that is relocatable so that the assembler actually gets to pick the actual numerical address. But a lot of times we don't. We'll just go ahead and pick the random access memory address ourselves. And when we do that, we actually know what that number is. And it's easy to get that number confused with the data because the data is also 8 bits and the addresses are, well, they're 12 bits, but a lot of times we're only looking at the lower addresses that are less than 12 bits, maybe not even 8 bits. The first two banks are only, I guess the first two banks are, each bank's 128 bytes. So the first two banks would fit into 8 bits of address, but we have 32 banks. So we need all 12 bits. Okay. So in the C block, we're gonna call this, we'll call this XX, and then we'll write YY and ZZ, and then we'll write end C block. Now, what this is going to do, this is going to assign the address to XX of 0x20 and the address of 0x21 to YY and the address of ZZ 0x22, hex 20, 21, and 22. This is their address, okay? Now, if we look at back at our memory map, so I'm going to switch the share from this side to this side. And we go to where we have our memory organization, chapter 3, and we scroll down to the banks. Where in this 32 banks is that actually located? Well, it is actually located starting here at hex 20. So the first byte here, hex 20, next byte, hex 21, and hex 23. 20, 21, and 22. Those are the 3 actual addresses. Those are the locations. So So you're looking at all the locations, just like you're looking at a street map of San Antonio. And there are 3 houses here at 20, 21, and 22 hex in bank 0. And that's now those, we've now named those houses house XX, house YY, and house ZZ. Doesn't tell us anything about who's inside the house. That's the data. And we're going to get the data and put it in the house so we will know what's in the house. But right now, we don't know what's in there because when you boot this chip up, the value in the random access memory locations is completely random. It's whatever randomly populates those storage locations, and it can be anything. So you can't make any assumptions about what, it won't be all zeros, probably. Guess it could be, but it's unlikely. You have no idea what it's going to be. But those are the locations. All right, let me go back then. We'll stop the share and we'll go back to the other one. Okay, so now what I'm going to do is show you how I would write code to put the values we're interested in. Now, where's our data? Okay, our data is over here. We define the data. Now, where did we get this data? I just made it up, straight out of the thin air. So one data is hex 53 and the other data is hex 26. Maybe I should do these in decimal just to keep them separate, but I'm going to do them in hex anyway. But I don't want you to get them confused. Okay, so that's the data. The addresses are 20, 21, and 22 hex. The data is 53 and 26 hex. See how easy it is to get the data confused? Because it looks the same. Now, in a 32-bit processor, these addresses would be 32 bits. So it'd be a little harder to confuse it with the data because it, but then your registers are 32 bits. So your data could be 32 bits as well. So it is still easy to get them confused. Normally, we just refer to our locations with the variable names. And we know that the contents at that location is our data. All right, so let's load up the data. So this C block stuff would be done before our code even starts. But now we're going to start writing code. So somewhere we usually have the address start. And then we've got some instructions. And then now we're gonna write the code to put the data in the register. Okay, so the first thing I want to do is I'm going to bank cell, and I'll bank cell XX. Now, what that's going to do is it's going to go. It knows based on how the C block information was defined. It knows what the actual 12-bit address is of XX, YY, and ZZ. And since I specified X here, it's going to take the upper 5 bits of that address and put it in the BSR. Now, what are the upper 5 bits of the address of hex 20 in a 12-bit register? Well, so if you look at it, so we have here's our 12 bits. So these are all divided into 4. And then we have another 4. So that's 12 bits. 1, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 0 to 11, 12 bits. Now, the lower 7 bits then would be 0 through 6. And then here, this is the upper 5 bits. So if we write 20 in, that's going to be, well, this is 0. So 0, 0, 0, 0. That's the lower bit. And then this bit is 20. So that is 0, 1, 0, 0, 0, 0, 0, 0. So if you notice, our upper 5 bits are 0. So that's going to put, this bank cell instruction is going to put 0 into the BSR. Remember, the BSR is only 5 bits. And so it's going to put 5 bits of 0 into the BSR. Then now, are we going to have to do bank cell again for YY and ZZ? Well, that's a good question. So generally speaking, if you're just writing this program for one of our class exercises, the answer is definitely no, you wouldn't do that. If you were at a company and you were writing this as some sort of generic piece of code that might be used by a whole bunch of other people in the company who might assign YY and ZZ to other locations, then you might want to bank cell them individually. But since you assigned them in order, starting at the first general purpose random access memory location in bank 0, you know that XX, YY, and ZZ are all 3 in bank 0. So if you bank cell XX, you're good for YY and ZZ as long as they're in the same bank. So I'm only going to bank cell one time just to sort of save that. All right. So now what I'm going to do is I'm going to take the data that we want, and I'm going to embed that in the next instruction and load it into the W register. Now, how am I going to do that? Well, I'm going to use one of my literal instructions, and I'm going to use the MOV literal to W. And remember, that only has one operand, that's the K, and I can specify a byte. And what byte am I going to specify? I'm going to specify my data right here, this data, 0x53. So I'll just write down here, 0x53. That's data. Load the data for XX. Now that's not the address of XX, that's the data we're going to put at that address. So we have a house that we call XX house. And now we're going to put inside the house hex 53. All right, how do we get that inside the house? Well, now we're going to use one of our byte-oriented instructions. This was a literal instruction. Now we're going to use one of the byte-oriented instructions, and we're going to use the MOV W to F. MOVWF. This one doesn't take 2 operands. This one doesn't take 2 operands either. Only one operand, F. What is F? F is the file register. What is the address of F? 20 hex. But we're not going to use the address. We could, but instead we're just going to use the name, so we can so when we read our program, we can make better sense out of it. It gets really confusing if you use the numbers, and that's why we have an assembler. If we didn't have an assembler, then we could just compile our own machine language instructions and just have all numbers on the page. But my goodness, it would be difficult to remember what all the numbers were for all the operation codes and for all our memory locations if we have a bunch of variables. But I can remember XX, so I'm just going to put XX here. Now, that loads up the 53 we put in W. Now that W goes into X. And so now X has 53. We don't know what it had before. Whatever it had before has been overwritten and destroyed and replaced entirely by hex 53. All right, now we're going to do the same thing for the YY register. We're going to do move literal to move W, and that's going to be 0x26 because that's what we decided over here to put in it just arbitrarily. Okay, so we're going to put 26 into W, and then we're going to move W to F, YY. Now, I could write in here 0x21. That'd be fine. It is exactly the same thing because we've defined YY in the C block as being 21, which means it's now assigned to that location. But it's a lot easier if we just use YY because then we'll kind of know, okay, that's X, that's Y. Easier to keep track of. So we go ahead, question.
So that constant block doesn't actually address anything in memory. It just associates whatever you have that value as, whatever that name is. and you're just assigning it to memory at the very bottom right there.
Yeah, that's right.
Okay.
Now, I think it's possible in the C block that we could have done a value out here of 0x53, and I don't know if I don't think there's any initialization software that gets created to do that though. So unlike C, you can't initialize these things typically. Now you can. There are some compiler directives that will do some of that for you. Like if you want to take a block of memory and fill it up with FF, so make all the bits 1, or fill it up with all zeros, or fill it up with some pattern like AA or 55, you can do that. You can write a whole block of memory a certain value. There's a compiler directive for that. But I don't think you can initialize these in the C block. I'll have to double check, read about the C block in the assembler manual. If we can even find the assembler manual anymore. Yeah, but that's right. You don't get to initialize those values. And what I want you to think about is this: when you flash your code into the chip, the only thing that's in the chip are the actual instructions that got turned into actual numbers. When you hit reset or when you power up the chip, your code begins executing at the beginning of your code. There's no other code that runs first that gets everything set up for you. When you're an assembler, it's just what you wrote. Nothing else is there. And so the idea that something would magically write over the random data that pops up in every RAM location when you power it up, that it would be a false assumption. There would have to be an actual set of code written to do that. And since you didn't write it, no code exists. And the compiler directive, some compiler directives do create code, but you would be able to see that code in your disassembly listing. You'd be able to see what happened. And there is no code like that written, because otherwise, well, you wouldn't be able to debug your code then if you didn't know what other code the compiler had done in your behalf. So yeah, so that's right. This is as bare metal as it gets. Did that answer?
So I just want to.
Yeah, go ahead.
Oh, sorry. I just wanted to make sure. So does that mean the C block is just establishing address lines?
It's doing is associating a number with a variable with a name. So you could also, instead of doing the C block, we could forget the C block and we could just do this. We could say pound define XX 0x20, pound define YY 0x21, pound define ZZ 0x22. And this would do exactly the same thing. We can also use the equate. We can do I think it's XX, I think it's equate XX 0x20 and equate YY 0x20. I don't know. So there's several different ways you can set these up. But yes, that's what that means. Yes. All right. Anybody else? So that's why your assembler has no idea whether you're thinking of XX as a unsigned number, a signed number, or an ASCII character, or what, has no idea. So you have to keep that in mind when you do math. If you put in what you consider to be 2's complement numbers, then you have to check for overflow by checking the 2's complement overflow. And if you consider an unsigned, then you have to check for overflow by checking the C bit. But and on this chip, there's no V bit, so you got to do it yourself. All right. Okay, moving on. So so now we have these values loaded up, and we don't have to put anything in ZZ. But if you really wanted to, if you really wanted to, you could use the clear instruction. And I'm writing these little dashes here. They shouldn't be there. You don't put those in when you write code, but I don't know. So we could do CLRF ZZ. And that would clear it, but there's no need to do that. Okay, now that we have everything loaded up, let's see how we would actually write code to switch these numbers around. So this would happen up above. We'd get everything set up. We get our variables defined. We get them all set up. And then somewhere down here, we're going to swap. For some reason, we're going to swap locate what the contents of XX with the contents of ZZ. Now, how do we do that? Well, so there is a fancy way to do it without having to use a scratch register using exclusive ORs, but don't worry about that. And actually, there's if the values are identical, it gets you into trouble. So that's the only exception to it, I think. But we're going to do it the old-fashioned way, and we're just going to use the scratch register. And here's how it would look. So now we're going to do, we're going to first bank cell. Let's say we'll bank cell ZZ this time. Doesn't really matter. They're all in bank 0. So if we bank cell any one of them, we'll get 0 in the BSR and we'll be fine. But we do have to make sure the bank cell is set up, because we could have been doing other things up here that would have changed what was in the BSR. And now we have to make sure that it's back to what pointing at our variables. All right. And then we're going to take the contents of X. So MOVF, we're going to move F, XX, and we're going to load it in to W. Now we can write a 0 here, or we can write a W. Doesn't matter. Either way, the assembler knows that if you write W, it means make that D bit a 0, and if you put F or 1, then it makes it a 1, and that stores it in the file. But in this case, we don't want to leave it in XX. We want to move the contents of XX, and the contents of XX is now 53. Okay, so we're going to move that 53 into W. So we're going to take XX and we're going to move it to W. We'll make that a comment. All right, now what we're going to do is we're going to take W, MOV, W to F, and we're going to put it in ZZ. That's our scratch register. So that take now both the X register, the XX file random access location, and the ZZ random access location or file register, whatever you want to call it. Both of those have 0x53 in it. They have hex 53. They have the same value. Now we're going to move YY into W, and we have to put the W here. And then we're going to MOV WF. Where do you think we're going to go with this value in Y, and that's in W now that we took out of Y? So remember, we're switching the contents between X and Y.
I put it in X.
That's right. We're going to put it in XX. And there is no second operand with this instruction. Okay. Now, if we had not saved the value in XX, we would now have just destroyed that value. And so we don't want to do that. So we in this case, we saved it in ZZ. So now what we do, but now YY and XX have the same value. And what is that value? Well, we loaded 26 in Y, so that's what's in both XX and YY. And 53 hex is in our scratch register. So now we're going to get our scratch register back into W, move F, ZZ, W, and then move W to F. We want to put this in YY. And now we have swapped the contents of X and XX and YY with each other without destroying either one. Does that make sense? Did everybody follow that? So we had to do 3 steps. we had to define our variables using, say, a C block. We had to preload them with the data we were interested in having there. And then for some, who knows what reason, later in the program, we wanted to swap the contents. Now, we may have modified the contents since then, and that would be fine. Whatever the modified contents were would still be in those registers. So maybe that's what we wanted to switch, who knows? But in any event, if we hadn't modified them, we're just gonna switch them, then they would still have the 53 and the 26.
So Professor,
Yes.
if being as we originally called bank zero in the beginning, are there call functions that would pull away from bank zero or where we have to redo bank cell or?
Yeah, let's say for some reason in the middle of this, we had called some subroutine to do something. And in that subroutine, we had used some memory locations we assigned to bank 3. Then when we came back, we wouldn't correct the bank, the BSR would still have 3 in it. So if we had, say, a call called junk, if we had that in here, you would have to do another bank cell when you came back to make sure there wasn't a problem in junk that screwed up our BSR. Yes, you do have to do that. But if you know that you're not going to interrupt this code, then you don't have to worry. Now, if that code could get interrupted with an interrupt, what do you think? Do we have to fix the BSR if that's the case? Well, the answer is no,
It
because you
should
would
just go
never
back to where
know.
it was.
Go ahead.
It should just go back to where it was because the interrupt just, says at any event, it just stops it and then it goes right back to where it was starting.
That's right. But the only reason that it preserves the BSR is that it uses a shadow register to save that value and it restores it on the return from interrupt. So because we might very well change the BSR in the interrupt service routine, but it doesn't cause a problem because the BSR is saved in a shadow register. In most micros, it's pushed on the stack. Everything that we are allowed to use in our ISR is pushed on the stack and it's popped back off and restored on return. But in this case, the hardware actually has special locations because we only can do one interrupt at a time. We can't nest our interrupts, can't interrupt and interrupt. But on, say, the KL25Z, we have 4 levels of interrupt and a higher level priority interrupt can interrupt lower level priorities. So we would need a whole bunch of shadow registers to make that work. And most chips don't use hardware shadow registers, but this one does. And it's actually faster and nicer, but it also limits us to no nesting of interrupts. But yeah, but that's right. If we did a call in there, we would have to restore, we'd have to do a bank cell. If we're using interrupts, that problem's taken care of for us automatically. Because it would have to be, right? We wouldn't know where to put the bank cell because we wouldn't know where we might get interrupted. Could get interrupted anywhere. So that would be unworkable. All right, so we're basically out of time. I'll probably do this more, but these 2 routines, so loading, well, I should call it preloading file registers with data, and then swapping 2 locations or 2 file registers contents. So we looked at code for preloading the file registers and also creating the variables. And we looked at how we would swap the contents once it's loaded up. So now on Thursday, we'll go over the program we're going to talk about, but I'm also going to talk about how we do an assembly language for loop using the decrement F skip on 0 instruction, how we pull on a bit. We've already looked at how we configure a register because we did that for the OSCON register, but we'll go over that again. And then we'll also look in the program for Friday, how we use the bit set and the bit clear instructions to flash our LED. Okay, any other questions?
Professor, you're saying that the 12 core registers are basically shared. So if you are in any bank and you change it, it changes the whole value.
Yeah, they're, so yes, so the core registers are, the only one of the core registers we're really going to use is the is the W register. But that the core register would include the W register, would include the program counter. It includes the indirect registers, it includes the status register, it includes the BSR and the PC latch high. But we're really not going to directly use those registers. The only register in the core registers we'll directly use for the most part is the W register. There's also random access locations that are mapped to every bank as well. And so if we look at the data sheet again here, so you see the registers 70 hex to 7F hex and bank 0 are also mapped here. So they're mapped to there, they're mapped there, here, they're mapped to every single bank. So this group of registers here are mapped to every bank, and this upper 16 are mapped to every bank. I guess they're really right here. Those are mapped to every bank. So these are mapped to every bank, and that includes the two indirect references, which aren't actually registers. The registers that they're composed of are here. The PCL, the status, the 4 indirect registers, 0 and 1, high and low, and then the bank select, the W register, the PC latch high, and the interrupt control register. Those are the registers mapped to every bank, and those are 12 registers, 0 through B. And then starting then at register 13 in every bank, these are the special function registers that relate to the modules. And the first 6, 7 banks have a bunch of them. The last ones are in bank 8, and after that there might be something in the last bank, but basically there aren't any others after that. But if they added more functional modules, then they might need to go to higher banks with these special function registers. But here you see, even in bank 12, well, say bank 14, you have these registers up here mapped, and the last 16 random access registers mapped. So they are mapped to every bank. Did that answer your question?
Would W register on bank 0 say be the same in data as bank 3 W register?
Yes. It is the same register. Mhm.
Off programming side, Friday, do we need to bring anything or have anything ready for Friday?
Just bring your board, and hopefully you've got the thing soldered on it. But if you don't, bring it anyway, and we'll get it soldered up on Friday, and then we'll do the lab. Okay. All righty. So we'll look forward. We'll talk again on Thursday, and I will go through the program. I might do a video because I have to go into the office and do my micro 2 lab. So I guess I could, well, maybe I'll do it. Maybe I'll do the video from home, and then I'll go in right after that. Yeah, I might do that too. All right. So if I do a video though, I'll send out an email, let you know what, I'll give you the reference for the video so you can watch that, but I'll probably do it live. Okay.
Professor, is there a test going to be next week?
I might slide that. We'll see. I'll tell you on Thursday.
Okay.
Yeah, I'll send out an email and I'll tell you. But yeah, if it's Thursday, we might do it Thursday. We'll see. I have to look at the schedule. I know the first 3 weeks kind of set us back a little bit. Even now, it's a little harder to do this online because there's no it's harder to get feedback because nobody's got their camera on. I can't see if you're confused, crying.
I don't want you to see my weakness.
Right. We don't see you breaking down. All right. Okay. Or pouring out a shot of whiskey, trying to dull the pain.
It's too early.
All right. Okay. We'll see y'all on Thursday.